In today's video, we're going to go through some sample problems covering the calculations that we commonly encounter in stoichiometry of formulas for compounds and chemical reactions and chemical equations. This is a continuation of the concepts material that we covered in Chapter 3 earlier, and these are a range of sample calculations and show us how we use those concepts in realistic situations. As we're going through this, we want to remember, keep in mind the mole, and we have a number of about 6.02 times 10 to the 23rd. It's a very large number. What that tells us is in any macroscopic sample, there's going to be a large number of atoms, and that will give us some sense of what we're handling. You don't need to memorize all these digits, but knowing 6.02 times 10 to the 23rd is a pretty helpful number. And but you'll have this available to you on an exam. Now, you're also going to want to have a periodic table handy. When you're doing calculations here, and a lot of work throughout this semester, will make reference to the periodic table on a very regular basis. So you have this, it would probably be a good idea to print this out and have it next to you at all times so that you can use it. You don't need to know the atomic numbers. You can look these up, and you don't need to remember all the atomic masses. Though as you do a lot more calculations, you'll start to remember some of these numbers simply by virtue of seeing them over and over again. And of course, you don't have to memorize all of the symbols, but it is very helpful if you do know at least the first few rows of elements, knowing the symbols and their associated names. It'll just make your problem solving a lot easier. And of course, there's time limitations on the test. And that while that time clock is ticking, it's better to spend the time working on problems and thinking through things rather than looking up names and cross-referencing symbols. If you do a fair number of problems, you'll start to pick these up pretty quickly. But it's good to make a good effort to remember the names and symbols. Now, there's a list in your textbook, a page that has all the names and the associated symbols and the associated molar masses. You may want to print that out just to have next to you wherever you're doing your work this summer. So you can have your periodic table, you have your calculator, you may have that list of elements, and that's something that's available to you in case you draw a blank or forget one of the elements, or you come across one that you're not comfortable with or not familiar with. So these are a few worthwhile things to have available. Most chemists have a periodic table, while most chemists probably have memorized the bulk of the periodic table. They still keep one readily available. So let's start off with a basic calculation. And let's look at a calculation of the molar mass of beryllium hydroxide. This is a good problem to start off with because beryllium hydroxide then it's a compound, and this is going to remind us back to Chapter 2 on naming and tying that in with formulas, because we'll need the formula for beryllium hydroxide before we can calculate its molar mass. So you'll remember beryllium is a metal, and it's in group 2, so it's an alkaline earth metal, and it's generally has a +2 charge on it. Hydroxide is a polyatomic ion, so that's a -1. And so from that, you should be able to deduce what the formula for beryllium hydroxide is. As we're going through and doing problems today in this video, it might be helpful to pause the video and see if you can actually carry out some of the calculations before we do them, and then you can even check some of your work and see if you're on track. So for beryllium hydroxide, we know that the formula is Be parentheses OH taken 2 times. There's 2 hydroxide units for each beryllium, as the hydroxide has a -1 charge and the beryllium has a +2 charge. Now, knowing that, we can go through and we can calculate the molar mass. We have 1 beryllium atom per formula unit. We have 2 hydrogen atoms and 2 oxygen atoms. So we take 1 times the atomic mass of beryllium from the periodic table. We add to that 2 times the atomic mass of hydrogen. And then we add 2 times the atomic mass of oxygen to give us 43.028. So if you punch the number into your calculator, that's the number you should be seeing. And you would recognize we need to round we need to account for significant figures, and in that case, that means we'll need to round this number. Of course, the first number, beryllium, is going to have 4 significant figures, but its precision is in the thousandths place. Likewise, for hydrogen, there's 4 significant figures and precision in the thousandths place. Oxygen has 4 significant figures. Its precision is in the hundredths place. And that value right there is the determiner for the number of significant figures in the final answer. Your final answer should have precision in the hundredths place. That is 2 places to the right of the decimal place. So therefore, we need to round the 0 and of course the next digit is 8, so we round up to 43.03. That is the correct answer in this case. As a simple rule of thumb, when you're going through calculating molar masses, in this course, if you're dealing with compounds, you can round your values to the hundredths place. That'll be a fairly uniform and easy way to handle your calculations. Another thing to think about as you're doing your calculations, and this is a very important factor to consider, do not round your calculations until you get to the end. Even though we're accounting for significant figures on our way through, we don't want to round our numbers. If you round your numbers, this can inadvertently lead to what we call a rounding error. Your answer can be off in the last decimal place by plus or minus a couple of digits, and that can obviously adversely affect your answer. There are calculations that we won't come across them in this course, but there are some chemical calculations which are much more complex, where if you do round your answers in between, the result will go catastrophic and you'll get meaningless answers. So it's just a good habit to build in, and it is important to do because it's the correct way to do things. Do not round your answers until you come to the final step. Now you keep track of significant figures throughout, but rounding the numerical value only occurs at the very end. Next up, we have a table, list of equations that we called out as important last time. These are the mass to moles conversions. So on our first equation, we have mass is equal to the number of moles of a substance multiplied by its molar mass. That is the number of grams per mole for that substance. That is a key relationship. From that, you can derive the second equation. The number of moles of a substance is equal to the mass of that substance divided by the molar mass, or in this case, multiplied by 1 over the molar mass. It's the same, mathematically the same thing. Those two equations, the first 2 equations are tied together. They're basically the same expression, just rearranged. And then the third and fourth equations likewise are the same. They're just rearrangements. In the third equation, the number of entities of a substance, that is, the number of molecules or atoms or ions, is equal to the number of moles of that substance multiplied by Avogadro's number. And then for a substance, the number of moles is equal to the number of entities, the number of atoms or molecules, divided by Avogadro's number. And then you can see again, we've multiplied by the inverse. This graphic illustrates a lot of the calculations that we've talked about, and this is a very good way to think about amount and mass and number relationships for compounds and the elements within those compounds. So we start in the middle on the left-hand side. The yellow box has amount of compound. That's related to the mass of the compound by the molar mass. And it's related to the number of molecules by Avogadro's number. And the amount of a compound is related to the amount of the elements in the compound via the formula that you have for that compound. So let's do an example. Ammonium nitrate is an important fertilizer. It's also an explosive, turns out. Ammonium nitrate is really good for greening up your grass. You can buy pure ammonium nitrate at the hardware store, but if you go to buy it at the hardware store, they do take your name because they don't want somebody gathering up too much ammonium nitrate because it can be used as an explosive. If you have a sample that has 2.5 kilograms of this compound, that is ammonium nitrate, how many moles of the ammonium nitrate do you have? And that will be important, for example, if you wanted to do a thermochemical calculation or a reaction calculation, or you wanted to know how much nitrogen will be available to the soil. Now, a couple of things to think about. We see the name ammonium nitrate. We're going to need to convert that into a chemical formula because the chemical formula is what we will use for our calculations. Also, most of our molar masses, when we express them, have grams per mole, not kilograms. And in this case, you've been given 2.5 kilograms. So this reminds us back to chapter 1 when we talked about prefixes. Kilo is 1,000. So in this case, 2.5 kilograms is 2,500 grams, or 2.5 times 10 to the third grams of the substance. So we'll want to do that conversion. Our first step is to identify the formula of ammonium nitrate. We have two polyatomic ions bound into an ionic compound. We know NH4 plus and NO3 minus are our ammonium and our nitrate, respectively. They each have a +1 or a plus-minus charge, so we just need one of each. Now, the next thing we'll need is the molar mass of the ammonium nitrate. We know how to do this. We just did this for beryllium hydroxide. We will need 2 times the atomic mass of nitrogen plus 4 times the atomic mass of hydrogen plus 3 times the atomic mass of oxygen. If you go look on a periodic table and gather that together and add them all together, you end up with a value of 80.04 grams per mole of ammonium nitrate. So to get to our final answer, moles of ammonium nitrate is the mass of ammonium nitrate divided by the molar mass of ammonium nitrate. 2.5 times 10 to the third grams divided by 80.04 grams per mole. We end up with 31 moles of ammonium nitrate in this case. Our next problem, we continue with ammonium nitrate, and as in an above calculation, how many atoms of nitrogen do we have in that sample? So in our 2.5 kilogram sample, how many atoms of nitrogen are there? Well, in this case, we're going to need Avogadro's number, but we'll also need to recognize that for each mole of ammonium nitrate, how many nitrogen atoms do we have? How many moles of nitrogen do we have? Excuse me. We have 2. So we carry out this calculation. The atoms of nitrogen that we will have in ammonium nitrate will equal the number of moles of compound, which in this case is 31, times the number of nitrogen atoms per formula unit. In this case, that is 2, times Avogadro's number, 6.02 times 10 to the 23rd power. And we end up with an answer of 3.8 times 10 to the 25th nitrogen atoms. It's a big number, but we expect that because we're dealing with a decent sized sample and atoms are very small. One thing, it's good to do a lot of calculations, but it's also good to take just a few seconds after you do a calculation and look at it and say, okay, does this make sense? And if it does make sense, get comfortable with the magnitude of the numbers that you're seeing. If you're comfortable with the magnitude of the numbers, then that'll help you in the future when you do a calculation. If you make a silly error, which all of us are prone to do at some point in time, then you can catch yourself. Okay, our next calculation. We have a sample of calcium carbonate, and the sample contains 7.31 times 10 to the minus 3 moles of calcium carbonate. Our question, how many grams of calcium carbonate are in this sample? We'll need to know the formula for calcium carbonate. We know calcium is an alkaline earth metal. Carbonate's a polyatomic ion. It's an oxoanion. And based on that, we end up with CaCO3 for calcium carbonate formula. So we'll need to go on and we'll need to calculate the molar mass of calcium carbonate. We've already done that a couple of times, so hopefully you're comfortable with that at this point in time. And the molar mass of calcium carbonate, which is the atomic mass of calcium plus the atomic mass of carbon plus 3 times the atomic mass of oxygen, will give us a value of 100.09 grams per mole of calcium carbonate. Now, once we know the molar mass, we can combine that with moles to get mass out. That was that first slide we looked at on equations. So here the mass is equal to moles times the molar mass, and we get an answer of 0.732 grams. In this case, the answer has 3 significant figures because we take one number with 3 significant figures multiplied by a number with 5 significant figures. Our answer should have 3 significant figures, which it does. Next up, we'll do one quick calculation on empirical formulas. Empirical formula, as we saw before, was the lowest whole number ratio of each element within the compound. It's an experimental number that's derived from combustion analysis. And while it's an interesting number, it's not necessarily the most helpful number. We'd always like to have the molecular formula to know the actual number of atoms of each element that are in the compound or within one molecule of the compound. And so we'll start off with experimental data. So we have a sample of a new compound, and this new compound is found to have an empirical formula of C2H5N. So that value would be obtained from our combustion analyzer. If this new compound is found by an experimental means to have a molar mass of 128.99, we can ask, what is the molecular formula of this new compound? Now, once we get the molecular formula, if you calculate the mass based on the numbers in the periodic table, you'll see it won't come out to be exactly 128.99, but that value is experimentally determined. This 128.99 is an experimentally determined number, so there will be a difference there. So first we have to calculate the empirical mass. That is the formula mass for the C2H5N species. So we take 2 times the atomic mass of carbon plus 5 times the atomic mass of hydrogen plus the atomic mass of nitrogen gives us 43.07 atomic mass units. Now, based on that number and the molar mass that we found from mass spectrometry for the entire system, we can take that ratio and we find out that the true compound actually has 2.99, which is very close to 3 units of C2H5N. So the C2H5N unit has a mass that's only 1/3 as big as the entire compound. So we've got 3 units of C2H5N per molecule of this material. That tells us that our molecular formula is going to be C6H15N3. Next up, we're going to talk about balancing chemical equations. We looked at this last time. We know how to write out a chemical reaction now. We write reactants on the left, products on the right. And we need to make sure that every atom is accounted for in the reactants and the products. We have to have equal number of atoms of each type in the reactants and the product side. Here are a series of 4 chemical equations that are not balanced. You can pause the video and then use the principles that we just learned and try and balance all 4 of these equations, and then you can start the video back up when you're ready to check your answers. Our first reaction involves calcium carbonate reacting with hydrochloric acid to produce calcium chloride, water, and carbon dioxide. In this case, we can start off balancing the calcium. We can see if we have 1 atom on the left, then we'll have 1 atom on the right. Carbon likewise is balanced, 1 atom on the left and 1 atom on the right for calcium carbonate and carbon dioxide. The next that we might look at is chlorine, and we can see that calcium chloride has 2 atoms of chlorine, so we'll need 2 hydrochloric acids. And with 2 hydrochloric acids, then we put 1 in front of our water, and then we end up with the following coefficients: 1, 2, 1, 1, and 1. Next up, we have the molecule propene. This is not one of the compounds that we looked at under naming. This is an alkene, not an alkane, so it's a little different. So you wouldn't know the naming for that compound. But propene reacts with oxygen to form carbon monoxide and water. We've got 3 carbon atoms in propene, so we'll need 3 carbon monoxide molecules on the right-hand side. We have 6 hydrogen atoms in propene, so we'll need 3 molecules of water on the right-hand side to produce 6 atoms of hydrogen. And at this point, then, we'll have a total of 6 oxygens, so we'll need a coefficient of 3 in front of the oxygen. Our correct coefficients are 1, 3, 3, and 3. Next up, we have lead-2 nitrate reacting with sodium sulfide to produce lead-2 sulfide and sodium nitrate. We can have 1 lead atom and 1 sulfur atom from each of our first 2 compounds that will give us lead sulfide. We'll have 1 there. And if we do this, then we'll have 2 moles of sodium nitrate in our reaction. Finally, we have a reaction that's a little bit more complex. We have ammonium phosphate reacting with magnesium hydroxide to produce magnesium phosphate plus ammonium hydroxide. With ammonium phosphate, we have 3 ammoniums and 1 phosphate. So we'll start off with the phosphorus atoms. 1 phosphate is on the left, but 2 phosphates are in our magnesium phosphate compound. So we'll need a 2 in front of our first compound, ammonium phosphate. And then next, with magnesium hydroxide, we'll need 3 magnesium hydroxides to give us the necessary 3 magnesium atoms for our magnesium phosphate product. So we'll have 2 in our first compound, a 3 on the second one. And then on our right-hand side, we'll have 1 for our first product. If we do this, we'll notice that you'll either have 6 ammoniums or 6 hydroxides, so we'll need a 6 in front of our final ammonium hydroxide. And the reaction is balanced. Next up, we're going to do a series of stoichiometric calculations. That is, we're going to take balanced chemical reactions and we're going to look at the mass and moles relationships that occur in those equations. And we'll also use this to think about more complex problems. Here, this flowchart shows the fundamental relationships within the reactions. So on the left-hand side, that left column of mass, amount, and entities relates to our reactants. So the most important piece is the center piece, the yellow boxes. The amount of reactants then through the arrow would relate to the amount of products. So the three boxes on the left-hand side then, or excuse me, the right-hand side would relate to the products. On the right-hand side, we have the mass, amount, and entities of products. And the relationship of reactants to products comes through the yellow boxes, that is, the amounts of substance. Those amounts are in moles. That tells us that we need to use the balanced chemical reaction to carry out this relationship. Our first problem will do the following reaction. And the reaction is balanced as written, just to make things easier for us to start off with. We have lead 2 nitrate. 1 mole of that reacts with 1 mole of sodium sulfide to give 1 mole of lead 2 sulfide and 2 moles of sodium nitrate product. In this case, if we react 0.35 moles of lead 2 nitrate with 0.35 moles of sodium sulfide, what is the theoretical yield of lead 2 sulfide in grams? We can do it in moles quite easily. In fact, it's a trivial answer. It should come out to 0.35 if you're paying attention. But let's do this in grams. So we need to know that the stoichiometric ratio in this process is 1 to 1 to 1 between lead sulfide and lead sulfide. Therefore, this reaction is at stoichiometric equivalence because we have 0.35 moles of lead nitrate and 0.35 moles of sodium sulfide. That's equal to 1 to 1. Therefore, that tells us that we expect to generate 0.35 moles of lead sulfide, lead 2 sulfide. That is our theoretical yield of our product. But if we want to convert this moles of lead 2 sulfide into grams, what do we need to do? Well, we need to have the molar mass of the lead 2 sulfide to convert moles into grams. So as we do that, we calculate that number out. It's 239.30 for lead sulfide, lead 2 sulfide. So 0.35 moles of the lead 2 sulfide times the molar mass gives us our answer, which is 84 grams. Now, we talked about more complex situations when things aren't just simple one-step reactions. We can have reactions in sequence where one reaction is followed by a second reaction where the products of the first reaction become the reactants of a second reaction. We also looked at reactions where we have what we call a limiting reagent. So in the case up above, for example, with this lead 2 nitrate plus sodium sulfide, if we had 0.35 moles of lead 2 nitrate but 0.6 moles of sodium sulfide, we would know that there was extra sodium sulfide around, more than we needed to carry out the reaction. So then the sodium sulfide would become the excess reagent, and the lead 2 nitrate become the limiting reagent. So in this case, then, we're going to start to look at reactions that don't match the stoichiometric ratios written down in the balanced chemical equation. And then finally, we'll look at reaction yields. We've looked at one case where we've predicted how much, and for the lead 2 sulfide case, how much material we expect to get, but the actual yield can be less. You'll never get more than you're supposed to unless there's something erroneous with your chemical equation, because, of course, we can't create matter from nothing. But the actual yield can be less, and based on that, we can calculate a percent yield. So let's start off with a simple reaction. Aluminum sulfide reacting with water to give aluminum hydroxide and hydrogen sulfide. The reaction is balanced as written, so we have 1 mole of aluminum sulfide, and we don't put the 3 on sulfide because aluminum has only one common oxidation state in nature. That's aluminum plus 3. So aluminum plus 3 in this compound then gives us aluminum sulfide with 6 moles of water, gives us 2 moles of aluminum hydroxide and 3 moles of hydrogen sulfide. Now, if we react 25 grams of aluminum sulfide with 22 grams of water, what is the limiting reagent and what is the excess reagent? We can't just use masses. We can't say 25 is greater than 22 because those are masses. The reaction is carried out by atoms, and so we need to know what the molar relation is. 25 and 22 are the experimentally measured numbers, but these need to be converted from those units into molar units. And then we can do a comparison with the 6:1 stoichiometric ratio of water to aluminum sulfide. Once we've done that, then we can calculate the number of grams of hydrogen sulfide that can be released in this process. Hydrogen sulfide is a gas, that's why we indicated it is released. Turns out hydrogen sulfide is an extremely toxic gas. It's actually more toxic than cyanide. It's not as dangerous, though, because you can smell hydrogen sulfide very easily. It's the rotten egg smell. And that smell is there for you to remind you to keep away from any environment that has too much hydrogen sulfide, because it can make you ill or it can even kill you. Now, which is the limiting reagent and which is the excess reagent? We have a balanced equation and we have masses. Let's convert the masses into moles. So we need the molar mass for aluminum sulfide. We know how to calculate that. And if we do that calculation, we end up with 150.16 grams per mole of aluminum sulfide. 2 times the atomic mass of aluminum plus 3 times the atomic mass of sulfur gets us there. Now, we have 25 grams of aluminum sulfide. If we take that and divide that number by the molar mass, we will get the actual number of moles of aluminum sulfide that we have in this system. We can do the same thing for water. The molar mass for water we can calculate fairly easily, and it is 18.02 grams per mole. 2 times the atomic mass of hydrogen plus 1 times the atomic mass of oxygen. So that's 2 plus 16 gets us 18. So if we take our 22 grams of water and divide by 18.02 grams per mole, we see that we have 1.22 moles of water. So even though we have a smaller mass of water, we have many more moles. But we still can't just use inspection to think about this. We need to go back to the chemical equation. We know the chemical equation. Let's go up one step and look at it. We have to have 1 mole of aluminum sulfide has to have 6 moles of water for the reaction to be at equivalence. So what we can do is we can say the theoretical reactant ratio is 6 moles of water to 1 mole of aluminum sulfide. The actual ratio is 1.22 moles of water to 0.166 moles. So if you do that mathematical operation, you see that we have a number of 7.3. That is, the actual ratio is 7.3 moles of water to 1 mole of aluminum sulfide. So what does that tell us? Well, that 7.3 is greater than 6. Therefore, the numerator is larger than the theoretical value. Water is the excess reagent. The ratio is greater than the theoretical value. So water is excess reagent. Aluminum sulfide is the limiting reagent. At this point, many of you may go through and think back to either high school or other ways you've seen this. The textbook sometimes even does this, where you can take each amount of moles of reactant and calculate the moles of product, and then compare and see which one would generate more product, and that's the excess reagent. It just turns out that that's more calculations that you need to do. And the more calculations, the more room for error, the longer it takes. This is the shorter way to approach this problem and will get you to your answer quicker. But both of them will give you the correct answer, whichever way you choose to do. As long as, there's not only one way to do a calculation, but the nice thing with chemistry is there is one correct answer. So as long as you're able to every time get the correct answer using your method, and if it's logically sound and not just an accident, that will all be acceptable as long as you can get the mathematically correct answer. Now we have the excess reagent and the limiting reagent. From this, we can calculate the amount of product that we can generate. So we can ask how many grams of hydrogen sulfide can be released. That's controlled by the limiting reagent. The limiting reagent is the one that determines the amount of product that you will get. So in this case, we go back to our reaction stoichiometry. We know we get 3 moles of hydrogen sulfide for every 1 mole of aluminum sulfide. And we know that we have 0.166 moles of aluminum sulfide. We have to have 3 times as many moles of hydrogen sulfide. So our theoretical limiting reagent, or our theoretical yield of hydrogen sulfide gas in this case would be 0.499 moles of hydrogen sulfide. That's 0.166 times 3. Now, the question asks us how many grams of hydrogen sulfide will be released. And so we need to convert grams into mole, or moles into grams. So moles multiplied by the molar mass will give us grams. We need to calculate the molar mass of hydrogen sulfide, which you can do quite readily. It's 34.08 grams of hydrogen sulfide per mole. Multiply it by 0.499 moles. And we end up with 17 grams of hydrogen sulfide as the theoretical yield. That's how many grams we could potentially release in this reaction. So next up, we can ask another question. Let's consider that same reaction, everything the same, but if we only generate 12 grams of hydrogen sulfide, what is the percent yield for this reaction? So looking at this, we go back to our definition of theoretical or percent yield. It's going to be actual yield divided by theoretical yield times 100. We pop our numbers in. Actual yield is 12 grams. Theoretical yield was 17. We multiply by 100, and we have a theoretical, or actual over theoretical, equal to 70%. There's a period put on there because the answer should have 2 significant figures. And if we simply wrote down the number 70 without the period, that would have only 1 significant figure. We want to delineate that clearly. That ends this video. You should make sure that you do plenty of practice problems through the Alex site. Make sure that you attend recitation sections and give yourself a chance to practice more problems on this area. It's a very important area and something with which you need to have good proficiency.